there. All right. So what we're going to start with, guys, and this is the stuff you don't have paid paper copy of yet, but I will give it to you eventually here. So how do we simplify radicals when they are not perfect roots? All right. So quick recap here. Perfect root. Perfect root is a radicand, right? The thing under the radical, which allows the radical to simplify to an integer, simplify completely, right? A perfect root can be written as an integer with an exponent whose power is equal to the root of the radical. To make that simpler, is 121 is a perfect second root because 121 can be written as 11 squared. 125 is a perfect third root because it can be written as 5 to the third. In other words, we can write the number that we have as a non-decimal to the power of the root. All right. And now here's the deal. The key to simplifying these, the way I'm going to show you, is based on knowing the perfect roots. Now, I would never expect you to memorize all the perfect roots because that is something that is really difficult to do and not needed because your BFFT Desmos can do it for you. All right. Now, I have on the page here in Miro, I have kind of a breakdown step by step with some images of what I'm going to show you in Desmos right here. So how do we find a list of perfect roots? Because every root, second root, third root, fourth root, fifth root, is going to have a different list of what numbers are perfect for that type of radical. All right. And so we're going to do square roots, second roots to start with. So the first thing you're going to do is you are going to type a variable, x, and put the exponent of the root. So it's a second root, so I'm going to put a second exponent. Don't worry about the graph. The graph doesn't help us, and it's all in this window here. So then we're going to click on the cog, and we're going to make a table. And then we're just going to list, the integers, positive integers, right? Just one going forward. And the second column here, the x squared column, guys, these are all the perfect square roots. Any of these numbers in the gray column here that you put under a square root will come out perfectly, will come out as an integer with no radical left over. And, you can see the nice thing about this is, let's say I want to know the 54th, well, 2,961, right? So using Desmos this way, which you will have access to on the test, allows you to make a list of numbers, the list of the perfect squares, perfect cubes, perfect fourths, whatever, very quickly and easily. So you don't have to memorize this list. You can always quickly get access to those list of numbers using Desmos there. All right. So that's the first part of this process, is being able to know which numbers are perfect roots. All right. The second part of this process is using a property of radicals, which I think is best exampled. That's not a word, I don't think. Demonstrated, there's the word I was trying to come up with, is best demonstrated by the character Blobby from the Hotel Transylvania movies. All right, we've been watching those recently with the girls, and they're pretty good. But Blobby gave me some inspiration for these notes here. The property itself essentially says, guys, if you have a radical with one term underneath, so your radicand is one term, you can split that radical up using multiplication. So there's the example, 5 times x times y squared. We can split that one square root into 3 square roots with multiplication in between them. And that goes both ways with that. All right. So we've got Blobby, all right, here. And if you've ever watched the Hotel Transylvania movies, right, or any other instance where you're working with some sort of living blob, essentially what Blobby can do is he can split up. He can break part of himself off. I think at one point he created like a child for himself out of himself, right? But the idea is whenever you split up a blob, the law of conservation of matter exists, meaning he can't split into 2 blobs that are the same size as the original blob, right? When he splits off, the blobs that he splits into are going to be smaller than the original. And you'll see in a second why this is important. But this only helps us if one of the smaller blobs, is a perfect root. All right, so let's apply our Blobby principle here with this example, the square root of 48. So the square root of 48 right now is not written with any multiplication. That's just a fully simplified answer. But we could rewrite the square root of 48 as the multiplication of two numbers. All right, so let's just go with the easiest one, 2 times 24. All right, 2 times 24. And now our Blobby principle, right, the radical property of multiplication, tells me that I can now split this one square root into two square roots. And notice those two square roots are smaller than the one we started with. Square root of 2 and square root of 24 individually are smaller than the square root of 48. All right. The problem is neither of those help me, because if we go back to our list of perfect squares, you can see 2 and 24 are not on my list of perfect squares. So that doesn't help me. So what we need to do is go back to the drawing board here and say, okay, what is a number from that perfect square list that the square root of 48 would be a factor of the square root of 48? And you can see we actually have two options. We've got 4 and 16. 4 is a factor of 48, and so is 16. Now, my advice to you is to always use the largest perfect square. So if we rewrite 48 to be 16 times 3, then what I can do is we can split Blobby into the square root of 16 and the square root of 3. Now, the square root of 3 we can't do anything with, but because the square root of 16 is a perfect root, the square root of 16 can become 4. And what we then end up with, guys, is the square root of 48 fully simplified is 4 times the square root of 3. This is considered the fully simplified form of that radical. The reason is because you now have the smallest possible number that you can get underneath the radical in that expression. If you used 4 times 12, you would have 2 times the square root of 12, which is not fully simplified. It's simpler, but not fully simplified. All right, guys. And so if you are asked for exact values, meaning no decimals, because if you go to Desmos, right, if we go to Desmos, let me just delete this here, and we do the square root of 48, you can see we're going to get an irrational decimal, which you would have to round. You can always check your work and see if you did it correctly, because why am I not able to click on the 3 there? 3? Nope. Come on. 3. There we go. Oops. All right, there we go. You can see, guys, you get the same exact decimal, which that is how you would check your work to know if you actually simplified it properly. But this right here, 4 square root of 3, would be considered the fully simplified version of 48. And the good news is it's the same process every time. So if I came down here and I looked at, let's just do 75. So square root of 75. So I need to split the square root of 75 into two numbers, and one of them needs to be a perfect square. So if I come to my Desmos list, oops, I got rid of my Desmos list, but we can make it again real fast here. All right. So if I come here and I go 1, let me flip my computer around so I can type here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? You can quickly make a list of perfect squares. And we ask ourselves, which of these numbers are factors of 75? Well, pretty clearly, 25 is a factor of 75. And if you keep going, nothing's bigger than 25. So we can rewrite 75, guys, as 25 times 3. Then Blobby can split into 2 square roots here. And the square root of 25 becomes 5 times the square root of 3. And so we get 5 square root of 3 is the simplified form of the square root of 75. So literally, guys, it's just this repetitive process. It's really using your technology, using Desmos to get that list of your perfect squares, and then using the radical property of multiplication, aka the Blobby property, to then split the radical, simplify the perfect root you do have, and the other one just stays as it is. That's the best we can do, right? We can apply this even in third roots, right? The only difference between a third root and a second root, a square root, guys, is we have to, come on, we have to change, we would need to change the exponent to match our root. And that's going to change. I don't know why I'm having such a hard time with my touch screen here. There we go. That's going to change, guys, all of our numbers. So notice when I change this to x cubed to get a list of perfect cubes, perfect thirds, that list is going to be different. So every time you approach simplifying a different root, you're going to need to redo that list and make sure you're looking at the correct set of numbers here because it can be very easy to get them mixed up. So if we look here, what's a factor of 32 that is on this list? Well, 8. 8 right there is a factor of 32. So I can rewrite the third root of 32 as 8 times 4. Then Blobby splits into the cube root of 8 times the cube root of 4. Now, this is, you got to be careful. Make sure you're bringing the cubes down. And the cube root of 4 doesn't do anything for us. The square root of 4 does something for us, but it's the cube root of 8, which is 2. All right, now this is where writing your answer carefully is important. You can always just leave the multiplication symbol there, but what you will see it written as is this. And that is why, guys, it's so important you take the root and you make sure it's tucked into that check mark. Because if you start getting that 3, that cube root, the third root, bigger and outside, that's going to look like the number 23 rather than 2 times the cube root. All right, so that is, there'll be some extra challenge problems that if you want to practice over here that I'll fill in, but that pretty much wraps up simplifying radicals. We now how to do them when they're perfect, and we now know how to do them when they are not perfect. Rewriting radicals as exponents and vice versa. The deal is a radical as an exponent is a fraction. And guys, just like zero exponents and negative exponents don't make any sense, fractional exponents, I think, make even less sense, right? You can't perform multiplication 2/3 of a time, right? You either multiply or you don't. There's no like partial multiplication here. So when we get fractional exponents, what we need to be able to do is rewrite them as radicals so that we can work with them. And actually, sometimes we'll take radicals and rewrite them as fractional exponents because that is easier. And guys, this is the same idea you've used in your inverse operations previously. Taking subtraction and rewriting it as addition or vice versa. And the same thing with division and multiplication. I can take 9 divided by 3, and I can change that to multiplication by taking the reciprocal of the 3, 9 times 1/3. So all we're doing here is the same process that we did with our inverse operation pairs previously. We're just learning how to do it with exponents and radicals. All right, and here's the key. The numerator and denominator of your fractional exponent become the root and the power of your radical. The one thing that's a little bit trickier here, guys, is that the power, the m, you can see the numerator, can either go inside the radical, as in the first example right here, or it can go outside the radical by putting that radical in parentheses, as you see here. They're equivalent, right? You can write it either way. When you're working with expressions, sometimes it's helpful to put the power inside the radical. Sometimes it's helpful to put it outside. All right. But this is pretty simple, straightforward stuff. So if I have a radical and we want to rewrite this as a fractional exponent, all right, I have the base x. That's not going to change. All right. We know, let me just make sure I got my color coordination right. Yep. Okay. So we know that the root is going to be the denominator of our fraction, and whatever the power is going to be the numerator. So x, the fifth root of x to the third, is going to become x to the 5/3 power. All right, it's literally that straightforward of a change. When you have multiple factors, you can either do them individually or treat them as one whole here, right? We know that this is a to the first and b to the third. And we also know that this is a root of 2. We got a couple of ninjas in this example. Doesn't change anything. There is my denominator, and I am just going to do it separate for both a and b. So a will change to 1 over. Oops, I got the colors backwards. Sorry, hold on a second. A to the 1 over 2 power, right? And then times b will get its own fractional exponent there to the 3/2 power, right? And that's literally what you're doing. Flipping the other way around, right? Just to show you this example here. So 9 is, we know, going to be the power, and 4 is the radical. So right away, I can set up a radical with a fourth root there. There we go. We know the base is going to be x. Now, where we have an option is, where do we put the 9? We could do that. And that would be a totally correct answer, to put the 9 inside, or guys, the 9 can go outside. Both of these would be a correct outcome of that fractional exponent there. Again, the only difference between the two is sometimes, based on what you're going to use the radical for, writing it inside makes things easier versus outside. But literally, guys, that's all it is. That's what we're doing there in rewriting those. These questions down below here, 1 through 4, I'm not going to go through those. These are situations where rewriting the fractional exponent in the correct way makes these questions able to be done without a calculator. All right. I guarantee you can think through these without a calculator if you know how to rewrite them. If you try to treat them as fractional exponents, there's zero chance. I could never do, no one can do a fractional, I shouldn't say nobody. Maybe there are some super smart people out there, but I certainly am not smart enough to do fractional exponents in my head. But if I rewrite them in the correct way, I certainly can do them in my head as radicals. All right. And again, I will fill in everything in the notes that we didn't get to here.